So let's see. Okay, so we have this. All right, so again, make sure that you guys. So I'm gonna like ask questions because again, it's gonna be your test, not my test, right? Okay, so again, what is the column space of a matrix again? It is the blank. Mhm. So again, column space. So recall that the column space of a matrix A is what? So call of A is equal to so you guys have to know the terms, right? You can't just like not know it. Well, that'll be the basis for the column space, but yeah, it'll be the span of the entire column. But yeah, I mean, yeah, if you take the span of the basis, it'll also be the column space. But yes, yeah, take the span, yes. So is the span of all the columns. Or you can, like you said, take the span of just the linearly independent columns as well. That would give you the column space. Okay. So we want a so for in our case, it would be the column space of A would be the span of the vectors. What vectors? Well, the columns, right? 5, 2, 3, 4, 3, 0, 2, 3, 0, right? Okay. So again, this is what the column space would be. Now, the question says to find an orthonormal basis for the column space of A, right? So what's some approaches that you can take in order to find it? Sorry? Grant-Schmidt? Yes, you can do Grant-Schmidt. However, let me just ask the question. I mean, you can do it, but you still have to do one more thing after that. Or you can do it in this step right here. The vectors in here, is this a basis for the column space? How would you know if it's a basis? So remember, what's the conditions you need for a set of vectors to be a basis? You need two things, right? Or one thing using the theorem that we talked about in class as well. The vectors have to be, first of all, linearly independent, right? That's the first condition. You can't have vectors in there that aren't linearly independent. that won't be a basis anymore. So they first have to be linearly independent. Yeah, exactly. So, and the second thing is the vectors have to span the space. However, for Rn, as long as it's linearly independent, it will span it. So all you need to do is just check if it's linearly independent. Okay. So again, you can just do Grant-Schmidt off the bat. However, at the end, you're gonna have to pick the ones that are linearly independent. You can't just have, as soon as you're done, you can't just like say all of these are the basis, okay? So we need a basis for the column space of A. So how do I take the, so okay, how do I find out which ones are linearly independent? Yeah, exactly. Yes. Perfect. So let's RREF it then. Um, let me take this again. So take this, RREF it, and if you RREF it, you're going to get this. 1, 0, minus 6 over 7, 0, 1, 11 over 7, 0, 0, 0. Okay. Now, question. What would be the basis of the column space now that you have this RREF matrix? Remember, which ones are the linear independent columns, right? No. So you can just use a calculator. No more REF steps. I only wanted that for the first. Yeah. Yeah, correct. It's the first and the second column. Why is it the first and the second column? Huh? Yeah. Those are the pivot points, right? So remember, yeah, exactly. So this one, you take the ones that have the pivot points or pivot columns. So this one corresponds to this one, and that one corresponds to this one. So these two are the ones that are going to be linearly independent. Okay. So picking the first two columns, we get the basis 5, 2, 3, 4, 3, 0. So the column space of A can also just be written as a span of 5, 2, 3, 4, 3, 0. Okay. All right. But now we have a basis for the column space. So now what is the last thing we need? We need it for an orthonormal basis. Just use what we talked about earlier, right? Use branch Schmidt, right? That would give you an orthonormal, it would take in a basis and then do the process, and then once you get the end of the process, it'll give you a set of orthonormal vectors, right? So let's do that. So here, let's see. So using, so now we need a orthonormal basis, right? Using Grant-Schmidt. So does everybody remember the process of Grant-Schmidt? So first of all, what do you first need in order to even use the Grant-Schmidt? We're talking about you use you have your W1, you said it. But in order to talk about orthogonal in the first place, what do we even need in the first place? I mean, in a vector space, can I just talk about direction whenever I want, or do I need something in particular? Uh, you don't need the transpose, but I mean, the transpose is related to what I was talking about. You need an inner product, right? Otherwise, you don't know what what something is a orthogonal or not. So the inner product in here would be the dot product, right? So we're gonna use the dot product first. So all right, so let's see, what do we have? All right, so we have 5. Uh, so if you remember the formula, I think so. So recall. So let's see. So recall we have. Go here. Let's see. This, right? So this is the Grunge-Schmidt process, right? So we need to do this. So we pick a W1, then do V2 projection of V2 onto W1, and so on and so forth, right? So in our case over here, um, dang, do we have that many? How many steps will we have for our Grunge-Schmidt? 2, yeah, just 2. So you don't have to like worry about all that stuff. So yeah, so just recall that I guess WK is equal to VK minus, I guess you can write it as a sum from J equal 1 to J equal 1 to K minus 1 of the projection of V onto W, J. Okay, so in our problem, we will use it on this guy. So I'm going to move this guy over. Okay. So first thing is first, we need our W1, right? So you can pick W1 to be whatever you want it to be. I'm just going to pick W1 to be equal to 5, 2, and 3, right? So once you have this, what's the next thing you need to do? You need to find your W2, which you do by, I mean, just use this formula, right? Just literally just plug it in and use it. Okay. So we can just use this to be, okay, so W2 is going to equal what? Well, it's going to equal to, and if I guess if we label this as V1 and V2, it's going to equal to V2 minus the projection of V2 onto W1, right? And what is this going to equal? Well, it's going to be 4, 3, 0 minus, does anybody remember what the projection is? You're right. So the projection, let's say V onto W, is going to be inner product of V, W over the magnitude. So I guess I can just look it up over here. I always forget the the yeah. So it's right here. So U inner product of V over the magnitude of V times V. Okay. Inner product of V2 W1 magnitude of W1 times W1, right? And then again, what was the inner product? Yeah, you pick V1 to be uh, you pick V1 to be W1, and then W2 you get it from this. Yeah, so it doesn't matter which one you pick to be your W1, as long as you pick that and then you make your other one your V2. That's all that matters. Okay, so you have this. What's the inner product again in Rn? Well, like I said, it's 4 is the dot product, so you take the dot products. And then you take the magnitude of this, right? So W1 would be 5 squared plus 4 plus 9, so 29, so 38, I believe. And then all of this would just equal to well, let's see. So 4, that'll be 20 plus 6 plus, it'll be 26 over, how do you calculate? Well, you take the inner product of W with itself, but since it's an Rn, it's just going to be the square root, so like this. So so in Rn, it's going to be the square root of each component squared, right? Like this. So you just do this. You just take like literally just, if this is x, y, just do the square root of x squared plus y squared. That's how you calculate it. And you add them together and take the square root, okay? Okay. So remember, in general, you calculate it using the inner product with itself. So how did I get it 38? 5 squared is 25 plus, oh wait, how did I get 38? So 5 squared is 25 plus 4 is 29 plus 3 is 38, right? That's right, right? Yeah. I thought for the denominator that it was just a dot product of W1. No. So if we go back here, oops. Not there. Right here. It's, well, I mean, you could, I mean, yeah, you have to multiply W1 at the end. So in general, it's a dot product of the vector with itself, but you can say it's just a dot product of W with itself, or just do what I just did. I mean, it's the same thing. All of it is just going to end up being the same thing. But yeah, you can say like it's the dot product of W1 with itself, and then square it, right? Okay, so I think you have to. Okay, so I see. So, whoops, my bad. So I see your point. I see what you mean. So this should actually just be 38, right? So it's actually the norm squared, yeah. My bad, but yeah. Yeah, I can write it down. It's no big deal. Okay, so let's write it down. So again, this is going to equal 430 minus, so the dot product between V2 dot W1 over, so the norm, yeah, so you're right, it's 38, like I said, but we'll do it right now. So the norm of W1 squared. Okay, that's how we defined it, right? That's how we defined the projection. It's not that why we would square it, it's how we just defined it. So again, uh, it's over here, right? This part right here is the norm of V squared. Uh, yeah, so it's just how we defined it. It's not that, yeah, exactly. So yeah, I kind of confused her because I confused myself there. But yeah, it should be the norm of it squared. Okay, again. Okay, so we're gonna have 430 minus the dot product between V2, which is 430, dotted with 523, divided by W1, which was 523, dotted with 523, right? So take the dot product. So let's move this on this side. Okay, so this is going to equal the 430 minus, so the top is going to be, like I said, 4 times 5, which is 20, plus 6, which is going to be 26, divided by 5 times 5, which is 25, plus 4, plus 9. And then you still need, yeah, that's right, and we still need the 5, 2, 3 here. There should be a 5, 2, 3 there, so let me make this small. This is always the annoying part, is doing this. So what is this going to equal? It's going to be 430 minus 26 over 38 times 523, right? So just keep going until you get a vector. So it's going to be 5 times this, or you can just simplify this to, so it's going to be 13 over 19, I believe. Correct me if I'm wrong. Again, I'm not a human calculator. Uh, so this would be 430 minus 50, 15, 65 over 19, 10. So it'd be 10, so it'd be 20 times, okay, so it'd be 26 over 19. And then this one would be 30, 30, 39 over 19. And then literally just subtract them at that point. So it would be 4 4 minus this gross thing right here. 3 minus 20, 29. Give me a second. So 26 over 19, and then minus. No, you I think as soon as you're right here, you can just jump to the correct answer. I think that's pretty fine. You don't have to show all this. The reason I'm showing this is because I'm literally doing this question for the first time live here. That I need to like know what I'm doing. But yeah, whatever this vector is, it's gonna. So this okay. So this vector is W2, right? Okay. So what did we just do right now? Big picture, right? So we have this vector W2 and we have this vector W1. So what did we just produce? Huh? Yeah, now those vectors are orthogonal now, right? So now we just need to make them orthonormal, which means we have to do what? The last step. Sorry? Yeah, normal. Yeah, take the unit vector, right? Make it, yeah, so take this. Yeah, exactly. So divide by the magnitude. So take the vector and divide by the magnitude. So just then after that, just find so find yeah, hold on a second. I think my Apple Pencil died. But yeah, so take W1 divided by the magnitude of W1, and then W2 divided by the magnitude of W2, and then those two vectors call them U1 and U2, and this is an orthonormal basis. So I see here, so if we do W1 divided by W1 here, this will give me 5 square root of 38 divided by 38 square root of 38 divided by 19, and 3 square root of 38 divided by 38. So this right here is the first one, so call this one U1, and then do the same thing by with the other one, so W2 divided by the norm of W2. By the way, don't worry, the numbers won't get this ugly. I think the reason they were this ugly is because I just literally just made a matrix, like I just said 5, 4, 5, 6, 1, whatever, right? So that's why it's coming. But I'll make sure for the one in the test it comes out nice. So I won't like I won't just like pick numbers randomly. So this one will become 11 times the square root of 2603 divided by 2603, 31 square root of 2603, and then minus 39 square root of 2603 divided by 2603. Okay, this is your U2, and now B, so B equals the set U1 and U2 is your orthonormal basis now, okay? So, don't, like I said, don't forget, just know the process. Don't like be bogged down by the numbers. I'll make sure the numbers come out nice at the end. It won't be this like this much of a like mess, okay? So remember, just get the column space, find which ones are linearly independent, use the Gram-Schmidt on those linearly independent vectors. What comes out should be the orthonormal basis for the column space, okay? Okay. So let's see. So the next one, right? So that was 2. Let's do 3. So 3 would be, so 3 says, so consider R4 with its standard inner product, right? And let W be the span, so here. So we have R4 with a standard inner product. Yeah, if you understand the process, you'll be all right. The homework is harder because you have all semester to do it, and it'll make you understand a little bit deeper. But yeah, so like I said, the review is just going to be this. One of the questions, like I said, I'll take out and replace it, but it'll still be things that you should know how to do. I'm not going to say the question is harder. It's not. It's just it's a conceptual type of question. So you really have to know what's going on in order to really understand, like to answer it basically. So I basically captured a lot of the concepts in that question. Yeah. So you just know the process and just you'll be fine. Don't worry. Uh, and let W equal the span of this. Find a basis for W complement. Okay, so there's a lot of things going on here, right? First of all, do you guys know what the orthogonal, what W with that little upside down T means? So you have to know this, right? You don't need, you can, yeah, orthogonal what? Orthogonal complement, right? So what's in this W? Like, I mean, so what's in it? Well, not a, well, the basis well, the basis that's in there, it is in there, but it's not just the basis, right? Uh, it's the set of all vectors that are what? Orthogonal to the vectors in W, right? So, so recall that uh, W complement is equal to the set. So it's the set of all vectors in W such that V dot, well, better yet, V inner product with W is equal to 0 for every W in W, right? Sorry, hold on. Not in W, that wouldn't even make sense. So it would be in R4 in this case, or R. It really is the one is in the vector space, right? Um, but it's a set of all vectors that are orthogonal to ones in W. That's all that means, okay? Okay. So now that you know this, let's put this over here. how do you think you'll find all vectors that are perpendicular to the ones in W? I guess I should also, I think in the question, it also says that the W is the small, it says it's the span of these two vectors, right? So do you think that if the vectors that are orthogonal to the vectors that are the span of that thing, then those vectors will be orthogonal? Like, this is what I mean. So say you have a basis, right? Say V1 and V2, okay? Do you agree that if W1 is, or I guess, perpendicular to V1 and W2 is perpendicular to V2, then, and I should say W1 again, then W1 is perpendicular to all linear combinations of V1 and V2? Yeah, I mean, it's true. So, so literally all you have to do is do this. So pick a, let's say a W, well, not W, let's make it, pick V and V and W, I guess, and yeah, just pick V and V. Or I guess in this case, V is in R4. So that means V has this form, right? It has V1, V2, V3, and V4, right? It has 4 components. So now that, and if I told you that this thing right here, I mean, this is the basis for it. So what do you think I'm going to do with this V in terms of these vectors right here? Take the inner product with V with both of those, right? And I want them to equal what? 0, yes. So let's see. So finding. So in the inner product in R4 is just the dot product again. So you're going to do V1, V2, V3, V4, dotted with 2, 1, 3, 0. And we want this to equal to 0, and V1, V2, V3, V4, dotted with 1, 0, 1, 0 is equal to 0, right? Because as soon as we know if it's perpendicular to those two, then it's perpendicular to every vector that's the span of it, right? Remember, dot product distributes, so we can do that. All right, so we get the system. Well, you're just gonna get 2v1 plus v2 plus 3v3 equals 0, and then you're gonna get v1 plus v3 is equal to 0, right? So solving 2, 1, 3, 1, 0, 1 for v1, v2. Oh wait, oops, I forgot that there's a fourth vector, 0 and 0. v1, v2, v3, v4, and we want to know when this is equal to 0, right? Or you can just take the augmented form. Taking augmented form, we have just solved 2, 1, 3, 0, 0. Sorry, this would be a 2. What am I saying? This should be a 2 by 1. 1, 0, 1, 0, 0. RREF it. So it'd be RREF. RREF calculator. So like I said, you can just use a calculator or whatever to RREF at this point. I'm not going to make you do it by hand. Well, I think so. Like I said, I'm doing all this live, and so it might be. I just need to RREF it. 1, 2, 3, 4, 5. So 2, 1, 3, 0, 0, 1, 0, 1, 0. Okay. So if you RREF this, what do we get? We get 1, 0, 1, 0, 0, 0, 1, 1, 0, 0. So from here, you can read out your solution, right? So from here, you can see that V1 is equal to minus V3, and V2 is equal to minus V3, right? So your solution is going to look like this. So V1, V2, V3, V4. So that's just going to be minus V3, minus V3, V3, and V4. So you're right, V3 and V4 are free. But at this point, all you gotta do is just do this. V3 times minus 1, 1, 0, plus V4. You just solve them, right? V1, V2, V3, V4. So that first row right here, that gives me V1 plus V3 is equal to 0. Solve for it and you get that right there. And then the second row you get V2 plus V3 equals 0. So you get that so this one, yeah, perfect. Okay. What was I doing? Oh yeah, I was reading out the solution. So V4 is going to be 0, 0, 0, 1. Okay, so any vector that looks like this is orthogonal to every vector in that space. However, all you gotta do is then take these are the bases now, by the way. So this one, I don't know, call them U1, U2. So then W T is just the span of -1, -1, 0, 0, 0, 0, 1. Okay. By the way, there was an easier way to do it. Well, quote unquote, easier way for R and Rn. So remember, for a set of, okay, so if you have a subspace of R in, you have its basis, right? Like how we did here, we just set up the equation. So I guess let me be a little more clear. So see here, this guy right here. So if let's say I were to set up the matrix 2, 1, 3, 0, 1, 0, 1, 0. So remember what did I say this W the orthogonal complement was? It's just the null space of the transpose of this guy, which is exactly what we have here, right? that this guy right here is the transpose of this matrix. However, I didn't show you this way because I might change the vector space. And if I change it, you're gonna have to do this method right here. Okay. So anyway, that's how you do this one. Okay. So remember, just take y is v3 and v4 free, because if you look at this guy over here, as soon as you choose your v3, it determines v1 and v2. And then it doesn't matter what you choose for your v4. It doesn't affect your solution at all. It doesn't affect the equations at all, according to this. So you're allowed to choose what v4 is, and as soon as you choose what v3 is, it determines what v1 and v2 is. That's why you call those free. So just a reminder. So reminder. In Rn, if W equals the span of, say, V1 all the way to Vn, right? Then W complement is just equal to the null space of, I guess, let me spew. And A equals, let's say, V1 all the way to Vn, right? So if your columns is that, so it's just this W column is just going to be the null space of AT. Okay. So just remember that. Okay, and then last but not least, the last one, number 4. Let V equal the vector space C from -1, the set of continuous functions on the interval from -1 to 1, and let I guess, yeah, so with the standard inner products. I guess show, I guess it's better to show. So show that x squared and x in V are orthogonal. So this one should be actually really fast. What do you think we'll do? So how do you show two things are orthogonal? Yes. So what's the inner product for the set of continuous functions again? The integral, yeah. So all you got to do is x squared minus inner product with x, which is going to be from -1 to 1. Yeah, I have to send them out, but yeah, for sure. I'll send this out. It'll be at the end of the lecture notes for sure. X cubed dx. So this would just be x to the 4th over 4 minus 1 to 1, which is just going to be 1/4 minus 1/4, which is 0. So by definition, it's or they're orthogonal. So that's all you got to do for this one. Okay. So I would suggest what did I know? Because so okay, so let me add an extra step. So it's because it's going to be the integral from -1 to 1 of x squared times x dx. And how did I know how to use the integral? Why to use the integral? Is because the inner products for the vector space of set of continuous functions is, remember, integral from a to b f of x g of x dx. This is the inner products. So you have to know this as well. Yeah. Okay. Just a quick thing. I would suggest you guys really practice this one. Okay. and I practice, well, not, oh, I guess not this one, but like this one, okay? Practice this one using the method, this method right here. Yeah, the dot product. Yes, number 3. Because it's gonna be the same problem. However, I might change the vector space, okay? So it might not just be Rn anymore. It could be polynomials or continuous functions or something like that. But the process is still the same, no matter what, okay? Okay, and know what a basis is for sure, and what it means for you to write a yeah, you get all day for the test. So know what a basis is for sure, and also know that in a subspace, if you pick a vector in a subspace, you can write it as a linear combination as the basis elements in that subspace. Okay, just keep that in mind. Okay, it's like a hint, kind of, for the mysterious fourth problem that I'm gonna give. It's timed as in like, yeah, 24 hours that you get all day. Well, there'll be some recorded lectures. However, I didn't record them all, unfortunately, but I'll give you the lecture notes for sure. And if you have any questions, you can just email me and we can set up a time to meet. So you can ask me questions there, or if you need any help. Just know know that every vector can be written as a linear combination of its basis elements. And if it's and I guess if, yeah, just know that. I don't. If I give any more, you're done. It's just gonna give away the problem. Okay. Yes. 6 through 9. I think it was 10 actually. So 10 as well. As long as you do 90% for all of them, you're good. Okay.
I understand